Well, welcome everyone to the day two of the workshop. So today we are going to see the introduction to components. I'm Vikram Kannappa of third BTech CSC and here with us
I'm
is
Ka- I'm Karthikeyan Venugopalan, second year BTech ECE from Sastra Main Campus. Hope you have enjoyed the day one of our 5-day workshop series, Step into Robotics Basic and Beyond. We are sincerely sorry for the technical issues you guys had to bear through in the last day. The issues have been resolved and we hope to have a very seamless and fun session today. Today we are going to be having a what sensor is and some simulations in TinkerCAD about the sensors. Okay.
Karthik. What are the sensors we are going to see today?
Okay. Before going into what are the sensors we are going to see, let's say as yesterday we know that what a sensor is. I'm saying what a calibration is. For a sensor, a calibration is necessary so that if there is some malfunctions, it can be corrected. So that we'll move to the types of sensors. There are various types of sensors like IR, smoke, sound, PIR, LDR, temperature, humidity, ultrasonic, and gas. But due to one hour time consideration, we are going to see only about ultrasonic, IR, and soil moisture sensor along with the temperature sensor. We'll have a glimpse of potentiometer, LDR, and buzzer also. Okay, let me dive into what an ultrasonic sensor is. An ultrasonic sensor looks like two eyes. Okay, before going into its working, let me explain its pin out. It has 4 pins like the VCC, which is the 5 volt, which gives the power to the ultrasonic sensor, and the ground pin. The trigger pin, which controls the transmitter, and the echo pin is going to control the emitter. I'm explaining what transmitter and emitter is right now. Okay, my video is visible.
Yeah,
I
visible.
think,
Go on.
Yeah, bro, it's
yeah.
visible.
Okay, this is an ultrasonic sensor, and this is a transmitter, and this is the emitter part. And this ball here contains the piezoelectric material. What's a piezoelectric material means? I think you have heard about piezoelectric effect. If you don't, I'll explain. A piezoelectric effect means when you place a certain kind of material called piezoelectric material and you apply any kind of pressure or sound on it, it produces a varying electrical signal. What happens in an ultrasonic sensor is when you give power to the ultrasonic sensor, it will create a sound waves which is by anti-piezoelectric effect, and these sound waves are emitted by the transmitter here. When an obstacle is detected, that sound waves are deflected and it is going to be received by the receiver here. This receiver again gives the sound waves to the piezoelectric material, so that piezoelectric effect happens and a varying voltage signal is produced. It will be looking like this in the presentation. You can see. I think by the simulation you can refer that the sound waves are emitted and are reflected, which can be received. So that now we will be doing some simulations on the ultrasonic sensors, and will see about some real-time explanations. Over to Vikramanna.
Okay, we will see TinkerCAD virtual output now. Okay, before starting, could anyone answer what is a microcontroller? So this is a TinkerCAD layout. A microcontroller is nothing but a small integrated circuit that contains a processor, a memory, and an input-output. Then you could ask what is a microprocessor? It's nothing but the memory part of the microcontroller. Now, what are the things required, Karthi?
I think we can do by an LED output, and we can use breadboard, ultrasonic sensor kind of things.
Yeah, okay, let's start. Now, we are going to first take Arduino. The available thing here is Arduino Uno R3. Uh, TinkerCAD is basically a good platform for virtually simulating things such as IoT and many other. The only thing is most popular products will be only available here. Only Arduino, but not Raspberry Pi like that. So we need Arduino board. Then we'll take breadboard. Then we require the key, that is ultrasonic sensor. This is HC SR04 sensor that could measure distance and receive things. Okay. Then could anyone tell what is Arduino Uno R3? That explanation. What is Uno? Uno is nothing that it is a Latin name that signifies one, and R3 is revision 3. The updated version of the Arduino is R3. So first I'm connecting VCC in the breadboard. It's just a simple CPP language, so no panic, easy to learn. So we are going to design a circuit now. I have connected the VCC. Next we are giving ground pin. The ground is connected now. And we can change the colors of the wires here. I'm keeping ground red and VCC, I mean ground black and VCC red. So this is VCC pin. We will connect this. Then we are connecting ground pin. Okay, basically we have connected things. Now we are giving connection for trigger pin as well as echo pin. So
Bro,
yes,
can you be a little slow?
slow. Okay,
Yeah, the people seems to have issue that you are going faster. Could you be a
okay,
little slow?
okay. So this is a basic connection here. We have just given VCC and ground pin connected. Uh, every time key is that a breadboard circuit should be proceeded as. If any short circuit happens, it will be resolved by not attacking any of the components we have used it. So next we are going to connect trigger pin. Before connecting it, I will tell what are these. These are the pins that with till symbol that you could see here are the PWM as Ashwin took yesterday. They are pulse width modulation pins, which simulate analog output using digital signals. So we are connecting trigger pin to 9, pin number 9. Okay, next we are connecting echo pin to 10. Okay. Now we have done with the circuit. If you want, as Karthi said, we will connect an LED for reference that we could find this is working or not. An LED consists of cathode and anode, where anode is positive terminal, you all know. So I'm connecting the anode to the 13th pin. And cathode to ground. Okay, we have done with the circuit. So now we should code. I'm changing it to text now. Yes, as I have said earlier, it's basic CPP code that everyone could easily understand. Void setup is a function that where you won't change it. Uh, that probably runs only once when the Arduino is start. We should that we are setting pins. And void loop is the main function that has the main logic and that will be continuously executing the code. So we'll add We should now analyze what we have done. So we have connected the trigger pin to PWM9. So I'm going to code it. Yes, now we have initialized the trigger pin to 9th position of the ultrasonic sensor. Okay, next, as we are not changing it, I'm using const. We have set the echo pin to, and then we are giving LED pin connection. I have connected it to 13, so okay, done with this part, and we are going to void setup. Here, pin mode, usually pin mode gives the output or input to the specific pin we have specified here. So it defines the pin. Here trigger pin is going to be the output as it's going to emit the ultrasonic waves. And the echo pin will be the input as it's going to receive. Fine. Then LED pin is going to be an output for LED glowing. These are very basic syntax that everyone could understand easily. Okay. Now void setup is complete. Now we are coming to void loop. Here digital write, you could see digital write. Digital write is nothing but we are writing uh, its low or high value. Okay. In void setup, we are going to add serial begin, which is the most important thing. I have left this. Serial begin is nothing but the baud rate. 9600 is the baud rate that is used for simulation purpose, for debugging purpose. Okay. For debugging, this is very important that the connection would perform with that computer. Without 9600 bit, we couldn't proceed further. That uh, without serial begin, data synchronization will not be there. So no default baud rate will be proceeded. If we leave this, we can't even proceed. So the code will be a great failure. Okay, now we will proceed to void loop. Void loop, we are having digital rate. Digital rate is high or low value that could control a component. So first we are setting digital rate of trigger pin low. We are setting this low because we are clearing the trigger pin value first. Delay thousands microsecond is given, sorry, 1000 millisecond is given that we doesn't require. So I want to reduce it to short. So we are using delay microsecond function. Rating it that we will be rating high or low. Whereas there is another, like, which another function, that digital read is there, that reads the state of the pin. So digital read is simply going to write. You could easily understand like that. So we have given high. So now we are going to declare duration and distance variable now. So you will realize for what we are going to. We could give yes, we could give now long we could even give here. Okay. Now I have initialized duration. Duration is going to store the duration of sound waves that travel. And distance is going to store the calculated distance in centimeter that based on the pulse of echo pin. So we will define it here. Per microsecond, and the 2 here states that the to and fro motion that the trigger pin is going to hit an object. The trigger that ultrasonic sound waves are going to hit an object and return back. So there is emit and receive function. So we are using by 2 here. Okay, now we could see our we are using serial function that there is a serial monitor below. You could see this here that while running the code you could see the output. This is for our convenience only. So I am giving distance such. Syntax is very important, people. So serial comes with capital S, or else there will be an error here. Okay. We are going to print distance in between of this statement, and we'll add up of centimeter. Okay. So we will give the LED function. We'll define it by using an if loop. If we could set if distance is greater than 30, that LED should blink like that. You can customize everything here. Digital light, right? LED pin to high. And I'm giving a delay function in between. So we could give half a second, that is 500. And LED pin to low because it's going to be a blinking process, right? So high and low, it will be okay. same half a second we would give here. So if we have written else, we could write no function. So need to pin to low always. Okay, and we will set timer here that delay for 1 second. Here 1000 millisecond is equal to 1 second, so we are giving delay function for 1 second. Okay, now code is ready. Let's run. Okay, what is the error?
Declare that now int and so like that.
Yeah, it's fine with the right. Yes. Syntax. Okay, now it started. So we'll check the output. See, the obstacle is placed on 3.4 centimeter ahead. So we are reducing it to our range. Okay, see the LED is blinking as we have given above 30 centimeter. It's 48.7 centimeters above 30, so that LED is blinking. This is a basic ultrasonic circuit that you could use. Instead of LED pin, you could also place buffer, and your interest only, you could make anything with this. Usually this is very simple to make and interesting too. So next we'll be proceeding with IR sensor. So Karthi, you could proceed.
Yeah, nah. Okay. Before going into our next sensor, which is the infrared sensor, let me clarify what are the digital and analog the name suggests. Basically, there are two main types of sensors which include digital sensor and analog sensor. A digital sensor usually gives a high value which is 5 volt or a low value which is 0 volt, which can be defined as in binaries 1 and 0. Whereas in analog values, they will give a varying pulse width modulations, which can be seen as Ashwinana said in the previous day. And we have two functions named read and write, through which we can manipulate our sensors. So we have four functions: digital read, digital write, analog read, and analog write. Okay, let's move on to our infrared sensor. An infrared sensor is more similar to our ultrasonic sensor. And let me explain its pin out before going into its working. We can see that there are three pins only here, which is one is VCC, one is output, and one is ground. The output pin is where we are going to connect it to a digital pin so that we can get the output. And VCC and the ground are the two pins which gives the power to the IR sensor. Okay, let me have my video here. I think it will be visible now. Okay. This is an IR sensor. I'm having it in my hands. You can see there is two kinds of bulbs here. The black one is the IR LED, which acts like the transmitter in ultrasonic sensor. This IR LED is going to emit IR, which is infrared light, instead of ultrasonic sound in ultrasonic sensor. This white color bulb is nothing but a photodiode or a phototransistor, commonly called as the receiver. If it is a photodiode, it is going to produce a varying electrical signal as per the infrared radiations received. Or if it is a phototransistor, it acts like a switch and turn on and off depending upon the receiving of IR light. When I place an obstacle,
Adriana, could you please pin the video? Yeah,
okay,
thank you.
no
Continue.
problem.
Continue.
Okay. Let me assume that my hand is the obstacle, and if I place my hand here, the IR's light is going to come here and then reflect back, which is received by the receiver. This is the LM393 comparator that is going to compare two input values, one from the receiver and another from the potentiometer placed here. We can adjust the reference voltage so that these two is going to be compared, and if the input signal is high, it is going to give a low value, and vice versa will happen. We can get the appropriate values through the output pin, and if we program as per, we can get the outputs desired. Okay, let's have a simulation on it. Before that, I'll show you how this happens. You can see from my PPT, the IR emitter is transmitting, and after an obstacle, it is going to receive. And the LM393 comparator along with the potentiometer is given in the sensor. Okay, let's think again. Over to Vikramana.
Yeah, before tinkering, I want to ask you all a question. So raise hands, the people who have Me phone, Xiaomi phone, mobile. Okay. The purpose here is Me mobiles have IR blasters within it. So IR blasters are nothing but smartphones equipped with IR blaster would act as an universal remote that you could control many components such as AC, TV remote, etc. So this is interesting, right? So let's tinker. Okay. This is a basic setup of IR sensor. So we have given the VCC of 5 volt, ground pin is setted, and anode that is positive of the LED is given to 13th as last we have seen, and out of the IR sensor is given to 9th pin. And this is an IR remote that most probably have seen many places. So let's see the code. As we have set the IR sensor pin to 9th position. So there is a IR function here, an LED to 13th pin. As usual, there is a setup and loop functions. We have fixed the baud rate. Then pin mode is going to define the IR sensor that we have given as input. Then LED is going to be output. Inside the loop, we have given digital read for the IR sensor. And if we get high, then LED should glow, or else without no deduction, the motion will not be occurred, right? So we'll see the execution part. Okay. If a key is pressed, LED blink. You could see, right? Any motion it could detect in that LED. So we are using many components in day-to-day life with included IR sensors over here. That have you ever questioned that while picking a call, you recognize that screen is turning on while you take it to your ear, take it to near your ear. That is the only point that having a proximity sensor. Proximity sensor nothing but a small IR sensor that is used for obstacle detection, and we are having wide range of IR sensor over here. Karthi, we shall continue with Travel Master.
Yeah, there is a common doubt that what's the difference between a sensor and a microcontroller is. A sensor, as we have explained in the previous day or today itself, a sensor is going to sense a physical variable that is present. If, as we have seen, an ultrasonic sensor is going to sense the sound, while an IR sensor is going to send the light waves. Similarly, in our upcoming sensors, they are going to calculate different physical variables, whereas a microcontroller is a device that is going to control various sensors or maybe output pins or anything. They are going to control these sensors, and we have an interface to control them. So that this is the difference between sensor and microcontrollers. And now we are moving to soil moisture sensor. A soil moisture sensor is classified as a resistive, capacitive, and time domain reflectometry sensor. I think my video is visible right now. Okay.
Yeah, that is visible.
Before okay, before going into
Bro, there is a
IR
query.
sensor, sorry. Okay,
What is a baud rate? BAUD.
okay, Vikramanna, I'm asking you to explain.
Okay. Baud rate is nothing but the serial communication setting up that your computer and the sensor should coincidentally work right, without which there won't be a proper code vision. So baud rate initially gives a serial communication between our computer and the sensor, that the microcontroller, without which we would not get a proper result, that such as incorrect data transmission or potential communication failure, such so like that.
Okay, now.
Karthi, proceed.
Okay. Let me explain the types, what the resistive means. Before that, I'll explain its working. Like this is a soil moisture sensor, this is the module, and this is what we call as the electrode. It's basically a resistive soil moisture sensor, and each sensor have their own name. This name is FC28. They have their own name depending upon their series number and their company name, whatever it may be. Okay. You can see like the LM393 and the potentiometer are same here also. But the difference is that we had a IR LED and a photodiode or a transistor here, but instead we are having an electrode here. So this is where the change begins. This, what happens is, if we power here means the electrode is going to be powered so that the current is going to flow through these two electrodes. If we give a connection between these two electrodes, the circuit is going to be closed and we can have a current through here. What we are going to be doing is, we are placing this electrode in the soil. If the soil is wet, there will be presence of water so that it will be carrying the current through it. We have a closed circuit and we'll have a high value. If the soil is dry, so that we'll have a very less content of moisture, so that only a part of a signal is going to be transmitted. So this is what is going to happen in a soil moisture sensor. If we go for a resistive soil moisture sensor, it is going to calculate the moisture depending upon the resistance between the two electrodes. If the soil is dry, the resistance will be high, and if it is wet, it will be low. In a capacitive soil moisture sensor, which I don't have in my hands, you can see in my slide, in a capacitive soil moisture sensor, there is no two electrodes, but it is a single one, and there is no separate module for here. The capacitive soil moisture sensor is going to calculate the dielectric permittivity in the soil, so that we can have a very clear and accurate value of our moisture. And the pinout of this is explained here. Like you can see the ground, VCC, and analog output. Here we are going to deal with a new term, analog. So we can have a varying value. We can see it in TinkerCAD, I think. After that, this is a resistive soil moisture sensor. We can have both analog and digital values depending upon which pin we are going to connect and which pin we are going to be controlled by the microcontroller. And as usual, we are having the VCC and the ground pins. This is the electrode and this is the module. These has to be connected in the configuration given here. Okay, then what is a time domain reflectometry sensor? Which means it is going to give an electromagnetic pulse, maybe a light or anything, and going to calculate the time difference, because the light speed is going to change with its refractive index. If the soil is wet, there will be a change in refractive index, so there is a change in the time domain. This is going to be calculated and give a precise input output than among the three types, so that we can have a time domain reflectometry sensor, but it's too expensive, so that we will be having a resistive soil moisture sensor for good values and a capacitive soil moisture sensor for high durability. Okay, after that, I'm asking Vikramana to put a buzzer in it. Before using the buzzer in our TinkerCAD, I want to say what a buzzer exactly is. A buzzer is nothing but an output device like an LED. It's going to produce electricity depending upon the, it's going to produce sound depending upon the electricity we pass. It can be classified as electromagnetic and piezoelectric. As I said in the ultrasonic sensor, you can know what piezoelectric is. A piezoelectric effect is going to be happened and anti-piezoelectric effect is happened, and through the electrical signal we can have sound. I am having a buzzer in my hands, and you can see I am having a 9-volt battery whose red and black, which is the positive and negative, are connected to yellow and white alligator pins. These are called as crocodile pins as we wish. If I connect these two to my buzzer like this, we can have a sound. Okay, we'll have soil moisture sensor and buzzer together in our TinkerCAD action. Over to Vikramanna.
Okay, as Karthi said, we are going to see the simulated output here. Okay, so this is a soil moisture sensor So I have set a soil moisture sensor here, and a buzzer is being set here. So first of all, we will discuss the purposes of using these. Other than agricultural activities, we could use the soil moisture sensor. Any idea, or are you having any ideas over here? Other than agricultural field. So we could use this in foundation monitoring, that while construction, it needs 75% of moisture to be settled there. As per ASTM, that American Society of Testing and Materials, a concrete slab should have 75% of RH value. So let's begin the code. Okay. Ground is given to the ground, and signal is given to the A0, which is analog reading. And we have initialized the buzzer to the 8th position of the digital pin. So we are declaring variables as moist value, float percent, and buzzer pin is set here. As said, we are defining the baud rate here, that could explain the speed at which the transmission occurs. And buzzer is given as output. Inside loop, the moist values received from analog read. For digital pin, it is digital read, and we have given analog pin here so that it's analog read. The moist percent is this 539 is that the calibration value that would vary in every temperature, altitude, and the sensor's production. 539 is general value that is a constant for calibration purpose. So we are calculating moist percent, and this is for our purpose to see that output in serial monitor. And for using the purpose of buzzer is when soil moisture sensor reaches the value 50, between 50 and 70, the buzzer could ring. That is defined by tone function. So I have given the buzzer for 1000 hertz frequency. Else, if the function fails, so it comes to buzzer pin no tone. Okay, let's begin the simulation now. Okay. So we are varying here. You could see the serial monitor output. It's 11.13. Slightly reducing, exceeded the value. $42. We should be a bit precise now. Okay, you could hear, right? So it would be most efficient in agricultural field. Also, this would help in less mosquito breeding in places. Actually, we could avoid it too. So if you keep this in backyard, it would be most useful. So we have designed the circuit ourselves, something we have invented, right? So next we'll be seeing next sensor. Karthik, please proceed.
Thanks, now. Hope you had enjoyed this TinkerCAD session. And now we are going to a different thing called a potentiometer. This potentiometer is one of the important instruments that you can see in fan regulators, radio volume adjustments, and in many kind of applications. Let's see how it exactly works. Basically, there are different types of potentiometer. We can have a rotary and a linear. Linear means it will be kind of sliding potentiometers. Rotary means we can rotate. I am here having a rotary potentiometer which looks like this. Okay. After that, you can see that there are some 0 to 270-degree rotation. That's what I am having in my hands. This is the potentiometer. And if you can see, I can rotate this like this. I can have a rotation in my potentiometer. What it will do is it will change the resistance according to our rotation and give us a regulated voltage signal to the output. Okay, let's check what is the resistance value of this potentiometer is. Inside this potentiometer, you can see in the slide, it will be like this. This black thing is called as the resistive path, and the white thing inside is called as the conductive path. There will be a wiper in between the resistive and the conductive part so that it touches the both. If we start rotating, it will change the resistance and the according voltage value will be seen in the output. I am here going to connect uh, a positive to the first and negative to the third. These red and black wires are from the multimeter. Okay, this is going to say us what the resistance of this particular potentiometer is. Okay, let me put it into a resistance scale. We can see that it is having a 107 kilo ohm, so that it can have a maximum resistance of up to 107 kilo ohm. If this is the resistance part, you can see the rounding like this. If I change this to the center, as you can see, like here, if I turn it, it's 108 right now. As I increase, you can see the value is decreasing, and once it reaches the point, it will give a 0 ohm. 0 ohm means we will have a short circuit here. Similarly, if I change the black to in the first pin like this, in the right side it will be 108, and as I decrease in the left direction, it will give a 0 value. Okay, now we can know that the potentiometer is going to change the resistance value. Now I am going to say how it is going to regulate the voltage. As we know, as I said in the buzzer, I have connected my 9-volt battery to yellow and white colors. Okay, what I am going to do is I am going to give supply for, first I set it to the voltage. I am keeping it in 20 because only we are going to give a 9-volt battery. So it will be sure less than 20. I am giving uh, batteries positive to the first pin and the batteries negative to the last pin, which is these two are the resistive parts. And in the negative of the battery, where I connected the white alligator, I am going to have my black alligator, because we can have the negative of the value, negative of the multimeter reading here. Okay, now I am completing the circuit with the multimeter wire placing here. You can now see the value is showing as 0. As I increase the values, okay, once I'll check the circuits. Okay, you can see now the values is changing. I think there is some glitches here. Yeah. Right now, as I change my value, the voltage is going to be regulated here. right? I think I have a better circuit. Okay, I don't know why it's not working, but it will show depending upon the circuit, it will show change the value. As I move it to the right side, the voltage will decrease. I think yes. I don't know why it's not okay coming. I'll handing this over to Vikramanna, and if the circuit works, I'll join you back. Vikramanna, going to the simulation.
Well, so potentiometer, you will be noticing around every several functions. So starting from fan and speaker and many other, so we could notice potentiometer function. So this is a basic simple circuit that represents the LED light here. So this is an RGB light. So we have connected to we have connected three potentiometers to the light of the wiper. So there is a 9-volt battery fixed here, and resistance is given. So we could start the simulation now. Here you could notice a cathode and LED that is for adjustment of brightness. So we have fixed it to the third potentiometer here. So let's see the output. You could see, right? So if we increase, the light gets brighter, and if you want yellow, we could shift more the proper mixing of colors. So if you want to dim it, we could again resist it back. So this is how Karthi circuit works. And Karthik, let's continue.
Yeah, I have debugged it. There is a small connection damage in the battery. Now you can see that the value is showing 9 volts right now as the potentiometer is in 0. If I rotate in the clockwise, the resistance is increasing so that the voltage is regulated and decreases. As I increase in the direction, it is going to decrease and decrease, and after when I completely close it, it will be showing 0 volt to the output, so that there will be a maximum resistance. As I said, 107 kilo ohm I think we had. Okay, let's move on to our next thing, which is temperature and humidity sensor. Okay, what exactly a temperature and humidity sensor? It's going to help us to calculate the temperature in the environment and the humidity also, both in a single sensor called temperature and humidity sensor. There is a value for it which is called as the DHT11. Why the name? Because DHT denotes the okay DHT denotes the denoting humidity and temperature values. Okay, I'm having wait okay I'm having a DHT11 sensor here, and this thing is nothing but to have a ventilation inside the sensor, and this covering is because to avoid the physical damage to the outside environment. Inside this we'll have a NTC. NTC is nothing but a negative temperature coefficient thermistor. Have you heard of the term negative temperature coefficient? If not, let me explain. What a negative temperature coefficient means is that if I increase the temperature, the resistance is going to increase. For a normal conductor, it is not going to happen. And if we increase the temperature, the resistance is going to increase, so that we'll have a less value of voltage as we increase the temperature. But in a semiconductor kind of things, if we increase the temperature, the resistance decreases, so as the resistivity also decreases, and we'll have a very high voltage in the output. I want to explain a voltage divider circuit here because it will be helping in both temperature, humidity, and LDR sensor. In a voltage divider circuit, we'll have a two resistance in series, and the output voltage is determined by the formula given below. In a DHT11 sensor, the R1 will be the negative temperature coefficient thermistor. This thermistor, actually how it works means, if the temperature increases, the resistance is going to be decreased so that you can get the value. Okay, let us assume that we'll having a high temperature, so that the resistance R1, which is the NTC, is going to decrease, and the R2 is as usual a fixed resistance. If the R1 value is low, the R1 plus R2 value in the formula is also going to be low. Therefore, as this R1 plus R2 is inversely proportional to the output voltage, we are going to have a very high voltage in the output. So that we'll have a denotation of high temperature. If the temperature is low, the R1 is going to be high and the R1 plus R2 value is also going to be high, so that the V output voltage is low, denoting a lower temperature. Similar to this, instead of R1, instead of NTC, we'll have a light dependent resistor in a LDR sensor. We'll go through it a little bit later. For now, we'll have a glimpse of what temperature and humidity sensor is. You can have a pinout here. Like in a DST11 sensor, we have 3 pins, which is the plus minus. Usually they are denoted as VCC and ground, and the output pin, which is going to give an analog signal, like we discussed in the soil moisture sensor previously. Okay, I'm handing the session over to Vikramanna for tinkering.
Well, we could see sensor, right? Is the screen visible, Karthik?
Yeah, na, it's visible
Okay,
now.
fine. As we seen earlier, this is a basic setup. Here you could see and power, ground, and V out. V out is the main function of the temperature sensor. So we could fix the V out in the analog pin A0. So let's see the code first. So we have initialized the variable to store the temperature in Celsius. That variable is Celsius, and in Fahrenheit we have used Fahrenheit. And in void setup, we have received the analog pin A0 as input, and we have given the baud rate. In loop function, we are using analog read to receive the analog pin value and store it in sensor value variable. Then we could see the map function here. Map function usually comes with map. Wait, I could write the syntax here. Map, this is a function that is used to convert one range to another range. So we are converting Celsius here, right? So we are using first parameter is value. Then we could pass the value to which it should be low. So from low, then it should be highest value. Okay, then the desired output we want to get, I will tell it now. So we are using again too low output and too high. Okay, the desired value comes in the temperature sensor. Wait, I could decode. Okay. See, the negative value is minus 40. That is the least value of the temperature sensor, and the most value is 125. So we have used minus 40 and 125 as the desired value. 0 to 1023 is the analog value that it could, the range of analog sensor. And this is the value that is to be calculated. 3.04 and minus 20 are the constants that required to get an usual output, without which we cannot generate it. So we have converted the Celsius to Fahrenheit, and we have printed in serial pin. Okay, now let's see the output. By starting simulation, we could see usually it is 25, that is room temperature. So we could see the room temperature, and room temperature in Fahrenheit is 77 approximately. So if we are lowering it, serial windows also changed. So hereby we could tell our sensors and our components are working too good. And The main purpose of the map function is only for calibration purposes. These values are only used for empirical calibration, that without which we couldn't get the desired output. Okay, Karthik, next sensor, please.
Yeah, thanks, now. Okay, guys, we'll have a loss sensor and a little bit starting upon it. Light dependent resistor. As I have explained in the voltage divider circuit, instead of NTC thermistor in our temperature sensor, we'll have a light dependent resistor which looks like the figure here, there. Okay. We have two types of light dependent resistors, which are photoresistive and photoconductive. Resistive doesn't mean that it is going to change the resistance, but it is actually going to calculate the change in resistance. But in photoconductive LDR sensors, they are going to change the conductivity, like in photoelectric effect. The free electrons are going to travel from the valence band to the conduction band. I think you all are aware of it. I'm going to the voltage divider circuit just for now, because to explain the light dependent sensor resistor. Okay, I think I have it now. Okay, in LDR sensor, the R1 will be the LDR, so that if there is a heavy intensity of light, the resistance is going to be decreased. As due to this decrease in resistance, as I have mentioned before itself, R1 plus R2 value is going to be decreased, so that the output voltage is higher. So that for heavy intensity of light, we'll have a high voltage. In vice versa condition, like when there is a low intensity of light, there will be a high resistance, and we are going to have a R1 plus R2 a high value, so that the Vout will be always low. The R2, as it is a fixed resistance, it's always going to be fixed in both in case of DHT and LDR sensor. And over to Vikramanna for tinkering the loss sensor in our today's session.
Well, we had a loss sensor, so it is photoresistor, that is LDR. Here's the connection. So this is the photo sensor. As usual, we had made the connection through, and as earlier we had seen, this is to an analog pin connection, and we have grounded the terminal 2. The advantage of this sensor is it doesn't depend on polarity. Even terminal 2 can be grounded. I mean, terminal 1 can be grounded, and terminal 2 can be used for VCC. This we have used resistor here because that photosensor itself changes the resistance based on light intensity, right? So that without any uh, stable reference voltage, we could acquire the value perfectly, so that we have grounded with a resistor placed here. So let's see the code. As usual, we have initialized the photoresistor pin, that is an analog pin, so A0. Then we had set at baud rate, after which in loop we are getting the photoresistor in analog read and storing it in sensor value variable, after which we are printing the value, and with the delay function we are completing it. So let's see the output here. So by varying, we could see the variation in serial monitor. That is the input that is being received. Okay. Basically, you know, right? Photoresistor sensor works in dark, that has high resistance, and in bright it has resistance drop. So the sensor is made up of a material that is called as cadmium sulfate or cadmium selenide. Uh, you could see in many places these sensors, that you could see this in street lights, etc. So mostly we are using the sensors every day-to-day life. So approximately we have covered the major popular sensors that is being used. So Karthik shall proceed.
Yeah, now this is I forgot to mention about the material it made. We can have different types of materials. We can have a cadmium sulfide or cadmium selenide, or we can also have a lead sulfide also. I am here having LDR. I think it's okay. LDR, which is made of cadmium sulfide here. And a beneficious thing in LDR is that there is no positive, negative pins and pin out like that kind of stuff. So that here we are completing our day 2 of Step into Robotics Basic and Beyond workshop. If you find this video very helpful, do like this. And if you have any queries, we will post the meeting link in the description so that you can join here and ask your doubts in our live session. You can follow us on Instagram and LinkedIn via the ID given here. Vikramanna, any words?
Yes, if any doubts, uh, do enter the meeting.
Adina, I think you can post the meeting link.
So tomorrow we will be seeing that LCD display. That's a major part.
And
So
about
we
motor
will have,
drivers, I think, right?
yes, yes.
We'll have like project demos in our day 3 and about computer vision in our day 4 and day 5. So stay tuned in our summer workshop.
Guys, I think Balaji has joined. Balaji, is there any queries?
Look, no doubts, bro. I just wanted to ask, like, right now there are only like 50 people watching now because there's a delay between you guys talking and the live stream. So it's about like 30-second delay.
Balaji has joined. Balaji, is there any queries?
So can we like join the meet for the next upcoming 3 days?
Anna Adina? Okay, now in YouTube we can end the stream. Balaji is asking a doubt like we can join in the meet itself.
Ah, Adi, one more thing. Like, most people who are watching this